Now we are going to talk about the applications of Mossbauer spectra only for iron complexes. Tin complexes we talk about later. So here we have two iron complexes, that is Fe, Fe2 and Fe, Fe3. They shows different magnetic behavior. As we change the temperature, their magnetic behavior also changes. So now first we will talk about Fe, Fe2. So the structure of Fe, Fe2 looks like this in the crystal form. So each iron atom is surrounded by 6 fluorine atoms. Like this. So now we'll take one iron atom. So each iron atom is surrounded by 6 fluorine atoms. Means the shape, the geometry is symmetric. Okay. So now we have an iron here. We have iron plus 2, that is T2G4 and Eg2. Because fluorine is a high spin complex, we have a T2G4 and Eg2, total 6 electron in Fe plus 2. So we have a T2G4 and Eg2. So now the electric field gradient of this one is unsymmetric because this is not in the symmetric in nature. 1, 2, 3, 4, 5, 6. So because of that reason, we will get a two-line signal for Fe, Fe2. So now this is at temperature 78.2 Kelvin. This Fe, Fe2 act as a paramagnetic in nature, paramagnetic behavior. But at 4.2 Kelvin temperature, this exists as a anti-ferromagnetic. Okay, so this Fe, Fe2 at 78.2, it exists as a Kelvin, it exists as a paramagnetic in nature. At 4.2 Kelvin temperature, it exists as an anti-ferromagnetic in nature. So this is spectra when we record at when we record at 78.2. So there it is a paramagnetic. Here we get this kind of spectra. So when we record the spectra at 4.2 Kelvin, we will get a 6-line signal in the ratio of 3:2:1:1:2:3. So in this ratio we will get a 6 peak, because when it changes from paramagnetic to anti-ferromagnetic in nature, the magnetic interactions comes into the picture. So because of those magnetic interactions, the further splitting takes place. So we have iron 57 in the excited state, and here we have iron 57 in the ground state. And this we generally don't see this split like this. So this also splits into 2 energy levels, and this splits into 4 energy levels. So this is plus or minus 3/2, this is plus or minus 1/2. In case of paramagnetic compounds, we generally don't see this splitting, only we see this splitting. But whereas in anti-ferromagnetic, because of magnetic interactions, we see both the splittings. Okay, so this is plus 1/2, this is minus 1/2, this is plus 3/2, plus 1/2, minus 1/2, and minus 3/2. So now here we'll see how many transitions. So this is one transition, 2, 3, 4, 5, 6. So here 6 transitions comes in the ratio of 3:2:1 and 1:2:3 ratio. So the spectra looks like this. So this is 3:2:1:1:2:3. So this is about the Fe, Fe2. Now we'll go for Fe, Fe3. So here iron is present in +3 oxidation state, that means T2G5 T2G3 Eg2. Total 5 electrons are there. So electric field gradient is symmetric. Now we'll go for the structure. This structure also same like Fe, Fe2. Here also each iron atom is surrounded by 6 fluorine atoms. Okay, so here geometry is symmetric, electric field gradient also symmetric. So now we will get a one signal for Mossbauer, one signal for one peak for Fe, Fe3, and this is also temperature dependent. At 363 Kelvin it exists as a paramagnetic. At less than 363 Kelvin, less than 363 Kelvin it exists as an antiparamagnetic. So when we record the Mossbauer spectra for Fe, Fe3 at this temperature, we will get a single line because there it's acting as a paramagnetic in nature. When we reduce the temperature, the paramagnetic will changes into antiparamagnetic in nature. So because of that reason, we will get a, here also we will get a 6-line signal in the ratio of 3:2:1:1:2:3. Okay, so this is about the Fe, Fe2 and Fe, Fe3. I think these transitions I have made a mistake. So this is allow and this is not allow. Plus 1/2 minus 3/2 is not allow. This is allow. Okay. So total 6 transitions comes here. And next we have low spin and high spin crossover. So the high spin low spin crossover can be explained by Mossbauer spectra. So what is the low spin? If del is greater than pairing energy, that is a low spin. When P is greater than pairing energy is greater than del, that is high spin. When del and P almost equal, that is a equilibrium of low spin as well as high spin. Okay, so this concept we can explain by the Mossbauer spectroscopy. So here we have one example that Fe SCN, I think I forgot that example. Sorry, FDTC thrice. So DTC means dithiocarbamato. Okay, so this exists as a equilibrium between high spin and low spin at all temperatures. So some complexes at high temperatures they exist as a high spin or low spin. At low temperature they may exist as low spin or high spin, but this complex will exist as a equilibrium at all temperature, high spin as well as low spin, equilibrium at all temperatures. So we have Fe plus 3, this is a T2G 5 EZ0. So this shows a 2-line signal. Okay, so the complexes which are showing equilibrium for high spin and low spin, we never expect them to show a single peak in the Mossbauer spectra, because there is always competition between the high spin and low spin, and they show average, means they will show either broad doublet or sharp doublet like that, but they never show a single peak. And next example, this is very important. We have iron 110 phenanthrolene twice, and SCN twice. So this is the complex we have here. So at 25 degrees centigrade it exists as a high spin. At minus 191 degrees centigrade it exists as a low spin. So this complex is having a +2 oxidation state. Iron is in a +2 oxidation state. Here iron is present in +2 oxidation state. +2 means 4s0 3d6. If we record Mossbauer spectra for this compound at a low spin means, sorry, at minus 191 degrees centigrade, at minus 191 degrees centigrade it is a low spin, right? So the configuration will be like this: 1 2 3 4 5 6. That is T2G 6 EG 0. So now here electric field gradient is symmetric, right? But geometry is not symmetric because we have here iron, SCN, sorry, this is 110 biphenol is bidentate ligand, and SCN and SCN. Though the shape is not symmetric, but electric field gradient is symmetric. So in this case we will get a doublet here. Okay, whereas if we record this Mossbauer spectra at 25 degrees centigrade, so at 25 degrees centigrade this compound is existing as a high spin, right? So high spin means here we have T2G 4 EG2, total 6 electrons. At high spin it exists as a T2G4 and EG2. So now shape geometry is unsymmetry and electric field gradient also unsymmetry, right? So here also we will get a doublet. The only difference what we will see at 25 degrees centigrade and minus 191 degrees centigrade, the counterfold moment. So at low spin stage this counterfold moment is less, because at least one is symmetric, that is electric field gradient is symmetric. But here electric field gradient also not symmetric. Because of that reason we will see more EQ. Okay, so this high spin low spin crossover is very important. This can be explained by the Mossbauer spectroscopy. So FeDTC thrice dithiocarbon, it exists as a high spin low spin equilibrium. That means where del and P are equal. So for that, when it's existing in equilibrium, there it will be average. So for average we will not get a single peak, we will get a double peak. And we have Fe 110 phenolphthalein and SCN minus. So at 25 degrees centigrade it exists as a high spin, and here we will get a more counterfold splitting. At 191 degrees centigrade it exists as a low spin, we will get a less counterfold splitting. And what about in between temperature? So here we have 25 degrees centigrade, here we have minus 191 degrees centigrade. So what about in between temperature? If we record Mossbauer spectra in between temperature between 25 to minus 191, it shows high spin and low spin equilibrium. At this point it is a high spin, at this point it is a low spin. So remaining temperature it exists in an equilibrium between the high spin as well as low spin. And next important thing is oxidation state of metal. So Mossbauer spectra can also explain the oxidation state of metal. The best example will take sodium nitroprusside, Fe CN5 NO 2 minus. Okay, so here NO is a neutral ligand. Okay, and now oxidation state of iron will be Fe plus 3. That means 4s0 3d5. So cyanide is a strong low spin ligand, strong field ligand. So 1 2 3 4 5. So we have a T2G5 Eg0. So this is a paramagnetic in nature, but in sodium nitrophosphatide is a diamagnetic in nature, and oxidation state of iron is Fe plus 2. Okay, so here what is happening, initially the oxidation state of iron is Fe plus 3, and NO is having 11 electrons, right? One odd electron will be there on neutral NO. So that one electron will transfer from the NO to Fe plus 3. Now it will become Fe plus 2 plus NO plus. When it become Fe plus 2, the extra electron will goes and pair up here. So now it's having Fe plus 2 oxidation state and T2G6 and Eg0 configuration. So now it became a diamagnetic in nature. So this can be explained by the Mossbauer spectroscopy, because here we will get a doublet, here also will get a doublet, but the EQ will be less here because electric field gradient is symmetric, whereas here EQ will be more because electric field gradient is not symmetric. So this can be transferred by d pi p pi bonding. So from here we can understand that NO, which is present in sodium nitrophosphatide, is a NO plus. It present as a NO plus, not as a neutral NO. Just like NO, it present as NO plus because electron is transferring from a NO to Fe plus 3. Then it will become Fe plus 2 and NO plus. Now Fe plus 2 is having a T2G6 and Eg0. Then it will become diamagnetic in nature. So this can be explained by the Mossbauer spectroscopy. And we have fourth one, SIS and Trans Geometry. This can also explained by the Mossbauer spectroscopy. So here we have two complexes, Fe CN4 Cl2. So this is Fe plus 2, negative 4, negative 2, plus 4. Okay, here oxidation number is Fe plus 2. That means 4s0 3d6. So in the both the cases, this is a T2G6 Eg0, right? So when we take a SIS geometry, Cl, Cl, Cn, 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 Cn. So this is a SIS geometry. And this is a trans geometry. So what we'll see here, in the both the cases, geometry is unsymmetric, but electric field gradient is symmetric, right? So in the both the cases we'll get a two-line signal, but the SIS one will looks like this and trans one will looks like this. So as we can see in this both the spectras, here EQ is more, here EQ is less, because as we see that cis compound is trans compound is more symmetric compared to cis compound. Okay, because of that reason, in case of cis compound we will get more EQ, in case of trans compound we will get less EQ. And we can also study iron complexes by using Mossbauer spectra. So we have Fe3 CO12. So the structure looks like this. Three, 4, 5, 6. So here iron atom is having a D8 electron configuration because iron is in the zero oxidation state. That means T2G6 and Eg2. So electric field gradient is symmetric. But if you see the geometry, so here this is almost equals to octahedral, but these two are not in a octahedral geometry. They are more unsymmetric in nature. So imagine that this is FA, FEA, B and C. So in the Mossbauer spectra we will see a spectra like this. Okay, this is for FEB and this is for FEC. Because they are in a unsymmetric in nature, we will get more EQ. Whereas this FEA, that is in a symmetric, almost equals to symmetric in nature. For that we will get a small peak like this. The final spectra looks like this. This is for symmetric Fe and these two for the unsymmetric Fe. So this is about the Fe3CO12, and we have two more examples here, same examples, H, Fe3, CO11, a negative charge. So here we have 3 irons, 1 2 3 4 2 3. So this spectra also almost equals to this only. So here also we'll get same spectra. And another example we have H, Fe, CO10, C, NMB 2. So this also same as these two. Here also we'll get a 3-line signal like this. And next another thing we have here, Fe, CO5. We know the shape of the FeCO5. Is trigonal bipyramidal, and here iron is present in zero oxidation state, that means D8 configuration. So T2G6 and Eg2. So electric field gradient is symmetric, but the shape is not symmetric. Trigonal bipyramidal is not symmetric. So because of that reason we will get a doublet for FeCO5. And another example we have Fe2, CO9. This is the structure for Fe2CO9. So if we record the Mossbauer spectra for this compound, we will get a doublet, and this is very important. So where at low temperature we will get doublet like this. One is unsymmetric in nature. One peak will be here, one will be here. They both are in unsymmetric in nature. If we increase the temperature, then it will become a 2-line signal with symmetric, means both will be same. So at low temperature it shows unsymmetric doublet like this. At high temperature it shows symmetric doublet like this. And this can also, Mossbauer can also explain pi bonding capacity. We have two complexes, Fe CN5 NO and Fe CN5 NH3. So in the both the cases D6 only. Okay, so here also this is T2G6 Eg0, here also T2G6 Eg0, but the Mossbauer spectra for this compound will be having a more EQ when compared with this compound. So as pi bonding capacity increases, the quantum fold splitting also will increases. So this is the order. NO is first, then CO, CN minus, SO3 minus 2, PPH3, NO2 minus and NH3. So as we go from this side to this side, EQ means energy, sorry, the gap between two line will decreases. As we go from this side to this side, the gap will, sorry, this gap will be increases, EQ will increases. So when we have pi bonding ligand, so that time we will be having a more separation between two peaks. When we don't have a, when we have sigma donors, that time we will be having a less EQ. So this is about the applications for Mossbauer spectroscopy for iron complexes. Later I will make on tin complexes. Thank you.